Ladies and gentlemen, and all the ships at sea. Great, thank you. Today's speaker is Dr. Minye Chen. He's with the Center for Analysis and Prediction of Storms at the University of Oklahoma. Yet another Sooner. He was invited by Barry, who is having terrible problems with coughing and things, so she's asked me to do the introduction, so that's what we'll do. Dr. Chen's PhD is in environmental health engineering from OU, focusing on flood and extreme precipitation events. He has 2 master's degrees, one in environmental and natural resource economics from the University of Illinois, Urbana-Champaign, and one from environmental engineering, also from Illinois, Urbana-Champaign. He has a Bachelor of Science in Environmental Systems Engineering from Penn State. The fun fact is that for 3 years, he was the CEO of a company called WT Care LLC, which provided data analysis and system optimization for environmental engineering projects and things like that. He actually co-designed and invented the hydrologic model CREST IMAP, a 2D hydrological model, and published 3 first authors as well as 7 co-authored papers in scientific journals. The title today is Variations of Hydrological Simulation Scales, Reanalysis, Prediction, Applications, Capacity Building, and Challenges. So, Dr. Chen.
Hi, everyone. Nice to meet you all. I'm currently not in my office, and I got a hard time to find a place that's quiet enough. So if my voice got interference by background noise, just let me know. Cannot hear it, just let me know. Okay, and then I'm gonna share my screen and let's start this. So again, I just a little bit briefly introduce myself a little bit. My name is Minye Chen. Right now I'm a postdoctoral researcher at Hydros Lab, which is a hydrometeorology and remote sensing laboratory, and CAPS, the Center for Analysis and the Prediction of Storms. Because I personally, my experience always around the hydrological modeling, so I basically use this chance to introduce my experience and some of the insights about hydrological modeling. Barry didn't introduce about the audience. So, how many of you has experience with hydrological modeling at all? Ever heard of it? There's one. Anybody in the crowd?
Yeah, there's 4 or 5 of us here.
Okay, all right. That's good. That's good. Yeah. So basically, that's what I do. But you probably will find something that you'll agree with me, something you probably won't. But we can put that into discuss. All right. Okay, so today's talk, I try to break down into this 5 segments. And basically, I will use, every segment has different features, and I will use my study as an example and telling, the insights and how I feel about them, about the hydrological modeling. So, for the people who have never touched hydrological modeling, I just briefly introduce what this is. This basically we use a mathematical model and program in the computer, try to simulate the hydrological cycle. If you know the hydrological cycle is the water as precipitation coming down to the earth, and some of the water got intercepted by the trees, vegetation. Some of the water will infiltrate into the soil. Some water will come down to the groundwater, and some of the water will become the surface runoff and flow to the river. And water in the soil and the groundwater will eventually go to the river too. Then we have evapotranspiration, which is, sun heating those water, they evaporate into the water vapor and go to the clouds. Then, the clouds moves, then becomes new sets of storms that become a precipitation. Well, that's more of the meteorology side. So if you put the hydrological cycle all together, that's basically a combination of the hydrology and meteorology, and that's why my lab's called the hydrometeorology lab. Right? So hopefully, we try to, combine the meteorology. Well, actually, we work very closely with the meteorologists, and and on this figure, it's a very simple diagram of the schematic, the process we try to model in the CREST model, which is our lab developed, and most of the hydrological model has those components. The water coming down goes to the ground and goes to the river and get back to the atmosphere. So so of course, when we're talking about modeling, they contains uncertainties. And that's, as a hydrological modeler, that's the things we're dealing with every single day. Uncertainties can coming from all of the places. First, it can come from the forcing data. We use meteorological data as a forcing, but those data might have some errors, right? So there's errors over there. And when we use those mathematical equations to compute the water movement, there are the parameters and factors in the equation. Those parameters might be off, and most of the time that's what we do. We try to make sure those parameters are correct, so we get a good output, a good results. And of course, at the end of the day, we're doing modeling. We cannot really 100% simulate what exactly happens. So if you look at the right hand side, this is very simplified. The soil column, right? The soil doesn't really look like that. It doesn't really have those two conceptual layers. And there's a subsurface flow, groundwater flow doesn't really flow like on the surface, and it has something to do with the soil profile. There might be gravels, so they will flow faster. Clays, they probably will not flow there. But if you don't have those data, you got to make assumptions. So there's structural issues there. Sometimes for the computational efficiency, you got to sacrifice some science, structural science there, and those things will bring those uncertainty too. And at the end of the day, the mathematical equation, right? If you look at everything in this three-dimensional level, yes, that's right. That works perfect, but you probably cannot. You probably cannot make them workable formula out of that, because it's all a differential equation, right? It's probably not linearly solvable. So who knows? There's mathematical problems that you put into the model. You just cannot really solve it. It cannot be programmed. So there's uncertainties, and actually, as a hydrological modeler, our job is to control those uncertainties as much as we can. So another thing is a hydrological model has scales, right? So you have those spatial resolution, from low spatial resolution to high spatial resolution. There's a lot of model run with 1 degrees, 1 arc degree in this Earth. There's another type of model can run with 10-meter resolution. Temporal wise, the same thing. There's a model function pretty well if you look at the monthly. For just look at the land surface water balance. Look at the monthly, and some model require 10 seconds of 10 seconds of the temporal resolution. And also, when we look at other scales, we can look at reanalysis. We look at the past. That's most often what we do. And also, we can try to see the future. Hopefully, we can use to see the future. And right now, it's pretty hot topic. Is we're working with a climate change. When we deal with climate change, we want to know what's happening in the future. That's more of the future prediction, and all those variations in the spatial and temporal resolutions. And if you're looking at the past or you want to look into the future, they all bring different kinds of uncertainty to your model and to your study. So again, so there's one thing we all to know, that there's no model can do it all. Okay, there's not one single model can do everything perfectly. There's no way. I think right now Wolf Hydro is pretty popular, which is like as a national water model. Even it's used as a national water model, it has a lot of things that it cannot do. It can function at a certain comfort zone, right? Every model has their comfort zone. Phantom, which is least flood from the University of Bristol. They are already applied to the global wide their model, but still they have their comfort zone. It's something they do well, something they don't. So again, just to emphasize, minimizing the uncertainty of a hydrological simulation, it's just basically what we do. At least that's what I do. So this I don't have to stress too much, because that's the thing. When we try to minimize the uncertainty, the first thing, that's actually the easiest thing we do, is doing the forcing evaluation. When we take those meteorological data, that's the first thing we do. We check if their precipitation is right or not. Right, so if they're right, close to the records, close to the rain gauge, then great, you find the right one. But here's the funny thing is, not all the climate data it's works in every case. Some climate data, some precipitation data is more accurate in the intense precipitation, like Hurricane Harvey, like Hurricane Durant. Some of the data has worked very well with that, and some of the data work well with works very well in the dry climate. So it has a better estimation on that. So again, based on your study, you gotta choose the one that's most accurate at that moment, at that time. And of course, those climate data, they are improving as we're talking right now, right? So there's a group of people that are working on those climate data, and they're improving them all the time. So maybe your study is back in 2014. Well, that group of data is not working so well back then, but right now for the newer case in 2022, they're perfect accurate. So there's no simple rule that say, oh, this one is better than the other. So that's, I think, as a hydrological modeler, that's the first thing you do. And actually, we publish a lot of. That's why the data evaluation paper, it's kind of abundant everywhere, but that's kind of required. We need to do this evaluation first. That will minimize as much uncertainty from forcing data. And also another interesting thing is, what if you don't have the rain gauge records, right? So a lot of countries, they don't have that much rain gauge records available, or they don't even have those instruments. What would you do with that, right? So in that case, well, you probably need some statistical methods to solve that issue, which I always use the triple collocation methods. So that one can basically select out some of the lower error products out of the three different products. And if you Google if you Google Scholar the triple collocation, you will find it out. It's a statistical methods that can help you to evaluate three different data sets, which measuring the same parameter or the same variable. then you can distinguish which one has more error, which one has less. So it's a useful tool just for the, once your study is outside of USA. In US, we're lucky. We're spoiled. We have so much data. We have so much data. We have so much observations, and we can always use them. And but that's not the case across the world. Let's start from the smaller scale to the larger scale. So the smaller scale, we can say, okay, inundation simulation is very small scale. It's very high temporal resolution, very high spatial resolution. So basically, you're focusing on like one event, right? You're looking at one event across like 3-4 days and see how this inundation happened, which is a flood inundation. And this is the CRISI map that in the introductions that co-designed this. Yes, it's we coupled the water balance module with a 2D shadow water equation together and try to simulate the 2D flood extent. So yeah, right. So we are not the only one doing this, right? National Water Model, they have a branch called try to do that using a national water model with hand to couple that together. And of course, the satellite could do that. The SAR could observe the flood extent, and also the Fathom, which is least flood, they all do that. But again, with different sources, they all look quite different. So first of all, USGS mapping is more of the ground observation. They interpolate the high water mark and make them into a piece of map, see where the water actually inundated to. But they all look very different. So which means that in this area, depends on the model that you select, you might get very, very different results. The depth distribution, it will be like all over the place, and the flood extent, it's some might be a little bit similar because Crest and Phantom and least flood, they were all like a model, hydrological model, coupled with the 2D water routing. So they look similar, but using other methods, you definitely look a little bit different. So this paper was published, and okay, so just today's presentation, most of the study are already published. So if you're interested, I can send you the link, or you can just Google Scholar my name. It's all there. So the thing is that this type of inundation study, yeah, it's visually cool, right? So it's like when I talk to like stakeholders, the people in the local who like to apply this model, that's what we want. That's what they want to see. They say, "Hey, wow, it looks so cool. Can we do this as a continuous map or like a local warning?" Well, the truth is, well, it's hard. It's computationally very, very costly. So because it's so hard to compute, it takes a lot of nodes. It takes a lot of cores. It takes a long time if you only have one laptop. So what it is once you have such a highly resource consuming model, that leads to when you try to calibrate it, you only can do it indirectly. You cannot directly calibrate it because each run takes a few days. You cannot. You just simply cannot just calibrate the parameters. So yeah, there's indirect ways, but are they the best way? I don't know. There's a surrogate model, a statistical model that help you to calibrate this giant monster. but still the results is there. And also another big thing is you don't even have a target to calibrate to. When it comes to the 2D inundation, 2D inundation, flooding, there's no reference data. You think that the USGS provide a map is the most accurate? Well, actually, even in their report, they say, well, we just do our best. It's not really representing the truth. So, so, so basically, you don't even have a reference that targets that give it to you to calibrate. So in most of the case, if you look at the literatures, most people look at this, they just trust the model. They don't even calibrate it. They just give it a go, and this is what it is. Because the community knows that there's no way you can make it perfect as a reality, because nobody even know what the reality is once the event passed. So yeah, another thing I just mentioned, the inundation depth is just very, very inaccurate. So if you look at the right bottom, that's just the plot between the simulation water depths and the USGS water high mark depths. They're not even linear. They're all over the place. So then we switch gear a little bit to continental simulation, large scale simulation. So the successful cases here was the CREST EF5, which has been online since 2017. It simulates the Conus stream flow at the 1 kilometer spatial scale. And I think it's every 15 minutes in temporal scale, recently improved to every 10 minutes. So when it comes to the continental simulation, then you need to worry about the parameter, because you're looking at a stream flow. You're looking at like a one-dimensional stream flow. At this point, if the stream flow is accurate or not, you don't worry about the depths of the water. Well, at least you cannot worry. There's no way you cannot. There's no way you can simulate the depth of the water across the entire country. You don't have that much computation power. But we simulate stream flow one dimensional. But at that case, calibration is more important, because you actually, in this case, you can. Because the 1D hydrological model is more efficient. You can actually run it for 10,000 times to make sure all the parameters is good. So here's another example of the CREST model. This the NSCE, which is a statistical score for how well the hydrological model performs. So what I'm showing right here is this is a calibrated model at over 3,000 USGS gauges, and there's a model performed pretty well, which shows there's a places that model performed very well, which it has a green dots, and there's a places that have red dots, which is concentrated in this area, in the mostly west side of the United States. So again, even after calibration, not every place works so well. Then something might surface up. There might be some structural issues. For CREST model, the structural issue is definitely for the dry regions. So because the model itself didn't consider the dry region very well, the soil and water interaction in the desert. It didn't really consider that much. So maybe other models can do it, but as far as I know, most of mainstream models they are not doing so well in a dry region. So that's how when you run hydrological model, that's how you identify your uncertainty. You eliminate uncertainty from forcing. Then you try to calibrate it to optimize the parameters. Once you think your parameters as accurate as it can be, then there's still amount of error still stays there. then it's very likely it's coming from the structure. Your model design, the model structure has something is not inside the component. Where very often, very often it's for the mountain region, because the low score region, but definitely one of them, Rocky Mountain. Often most of the hydrological model doesn't consider glaciers and the melting snow and the melting ice from the mountaintop ice cap. Because first of all, that's not that easy to put in there, and a lot of models didn't consider that. And also the other thing is the groundwater, because the groundwater we always try to simplify into the bucket, right? We simplify to the bucket, which is not real groundwater, because groundwater in the subsurface, it runs totally differently from what it runs on the surface. But we just don't. There's nobody. No one has that data, right? There's a studies try to couple like crest with mud flow. If you know mud flow, that's a groundwater transportation model. It can be done, but still mud flow require lots of data. Do you really have all those data to make it run across the entire country? Well, I would say even United States, that's not true. We are spoiled with data still in the United States. We cannot give a seamlessly running mud flow model throughout the entire continent. So yeah, so that's why there's a compromise. There's always a compromise, but we always try to do our best. So so the real-time system has been established. For example, the CREST EF5 has been established. The National Water Model has been established. They are running in real time or near real time. So it's a couple of minutes off the real time, then they give you the simulation. So the accuracy is it's not perfect. It's not the same as the USGS observation, but it has been praised by the National Weather Service, the National Weather Service. They have praised that those tools have been very useful for them to make a decision, but we're not at the stage that those computer modeling can replace a human, right? The National Water Service officials, they make the final decision. They look at the data and make an analysis. And yeah, again, you talk to stakeholders, say, you have this, you might, do you think, you can replace this office, then automatically running and give the flood warning by itself? No, it cannot, right? It's not there yet. We still need a human to read those data to make decisions. Yeah. And also another thing about this this continental scale simulation is that engineered structure in most of the cases is not considered in the model. As far as I know, this large scale simulations they put some if the data is available, right? But most of the time it's not there. In the global level, it's not even the case. You just don't have that, right? There in a lot of countries, those engineered hydrological structures considered as national secret. You cannot even get it. So that's not the case. So yeah, then we jump to the next topic is we do reanalysis and we can do future prediction, right? So this is one attempt that I published this year that using the QPF, which is a quantitative precipitation forecast to drive the hydrological model, which is giving you a couple of hours ahead of the event to simulate stream flows, to simulate the flood inundation. Well, here you can see this hydrograph you're familiar with hydrograph, basically it tells you. So basically, the lines are the stream flow. If you see a big flood, which is those peaks right there, and in this case, the gray area is the USGS observation, and the black line is using the actual the record weather rate data to drive the model. Then the rest of the lines are using QPF, which is forecast precipitation data. So it's quite different because forecast precipitation, it's very hard. It contains is a large uncertainty there, and the things is you cannot even pick and choose. Those uncertainties, it's not it cannot be eliminated because you're seeing into the future. You don't know what happened in the future, right? So the uncertainty is there. It definitely gonna carry through into your model. So is here. Using a different QPF give you different results, but not all the results are good enough. It can provide some insights, some useful information, but compared to doing the reanalysis, it's just far off. It's still a big chunk of uncertainty there that just you cannot eliminate. Well, I would say just the QPF is there. Uncertainty just carried over, and yeah, this is just a flood timing. It's because of the QPF has this uncertainty. Then the time, not only the quantity and the extent of the flood change, the timing is quite different from the benchmark, which is using the reanalysis benchmark. So yeah, well, if you're interested and to understand what this graph is about, I mean, I can send you the paper to read. Otherwise, I can jump over this one. So when we do future prediction, here's a successful application that we can do. Is we don't look at what actually gonna happen. Okay, we see the difference. We try to tell the trend difference. So this is a very successful cases that have been done by my colleague called Alan. He did a simulation. He just tried to calculate. First of all, he identified an index called flashiness. Flashiness is basically the slope between the peak of the stream flow and how long does it take to reach the peak of the stream flow. So that's called flashiness. So then he did the reanalysis and the future projection, and to calculate the index for each basin. Then it just subtract and calculate the percentage of change. See how the trend goes based on the climate difference. So this is successful because it evidently it picks out which region might be more vulnerable to the flash flood in the future. For example, the E, which is this area, is the South Plain, the Arizona and other Arizona desert, Colorado Basin, and also the South Plain in the Texas area. Right? So it can pick out which one has more change. And also, if we break down into the climate zones, it indicates that the tropical desert area will be more flashy in the future by the floods. It doesn't, well, that's the thing. Okay, why deserts have flood? Well, deserts can have flood, but most of the time it just being desert. Just when the flood comes, becomes really bad for the local locations too. So here's the future prediction. That's the things wanted to take away is that the QPF forcing has it's the QPF for the uncertainty is just too high, right? So it's not enough to provide accurate flood hazard forecast, right? So, we're not at the point position to say, hey, in 72 hours, your house will see 10 inches of water accumulating for 8 hours before it goes down, right? So if I give that kind of statement from the model, all those three numbers are wrong, right? There's three numbers. There's no way those three numbers can be right. It is the timing of the flood, the depth of the flood, the duration of the floods, and none of that can be accurate because there's so much uncertainty you cannot eliminate. So we're not at that point, but for climate change study, it's a very useful tool to find the trends toward the future because you can somehow you're just looking at the difference. Somehow the errors between the reality can be minimized. So okay, so I think that's basically most things I want to try to talk today, and of course at the end we also do a lot of capacity building. We do a lot of hydrological model trainings. We have helped the the East African nations, 4 nations, to train their staff and build a hydrological real-time hydrological model platform of the region. And also we have worked with Peru. Actually, that's my current project to basically do the same thing for the area. So yeah, that will be, I think I'm quite efficient. So that will be all for me today. Thank you very much. And feel free to contact me if you want to see something or something you want me to explain more. And also, any questions, feel free to bring it up.
Yeah, we have plenty of time for questions.
Yeah.
Anybody wants to raise their hand? Once you stop sharing the screen, we'll have to put your face up.
Right. I think Caroline
There we go.
raise her hand.
That's just right. You got it.
Yeah.
So, Joanne, you have
Sure.
a question.
So for your flashiness index or your colleague's flashiness index, the peak is pretty easy to pick. But on the rise of the hydrograph, I can see a number of different places where you would choose that point. How do you choose that point?
Choosing the rising star. Well, that just you from each hydrograph you can pick a base flow. So anything beyond that, like a two-year flood. So that's a definition of the base flow, the 2-year flood. That kind of return period is a flow. Anything beyond that, we call that a flood. So that's a starting point. That's once the stream flow beyond that threshold for each basin, then we pick at the starting point, then the peak, and yeah.
Okay, well, I have a question too.
Yep.
In almost every modeling exercise that I've ever been involved with for stream flow, and many of I've seen otherwise, the actual hydrograph is a single mode, whereas the simulated hydrographs very often have 2 modes, and you had the number of bimodal simulated hydrographs, and it's always explained as that's the difference between the slow flow and the surface flow, because the slow flow comes in a little later. Now, what do you think is going on with all that?
The multiple peak. Well, well, I know somebody explained that there's a surface runoff and subsurface runoff, but I don't think that's the case. I do believe that's more to do with first of all, the one I showed there, it was definitely caused by the QPF precipitation error. So basically, QPF has a second wave of strong precipitation after the first wave. Then after routing, the second wave shows up. And actually some of the QPF doesn't have it, for example, REP, right? But REP doesn't have it because the REP has a very coarse resolution. So all those little peaks kind of smooth out over the region. HRR, which is her is more higher spatial resolution, so it definitely has more peaks. And actually, I recently used other people's WAF output. WAF output actually creates a lot of those small peaks because because the WAF is a weather model. While a weather model as a model itself, it creates some spikes, more of the you can call it noise from the model. So that's what caused it. But from my experience with Crest, Crest shows model peaks with the correct forcing. But it didn't. It was just not true. It was not in the observation. That's mostly is the parameter. Parameter didn't get it right. So there is actually a parameter between the surface flow, and there will be a factor to multiply to the subsurface flow because subsurface flow is a little bit slower, right? So that parameter can be calculated, can be calibrated to make sure those two peaks can converge together.
Tweak the model.
Yeah, yeah. So you need to tweak it out because again, there's no way, there's not even a simple way to do the subsurface flow right. So right now every model that I know that can apply the Continental wise, it has to be it's the surface flow is just whatever they do, the diffuse wave, kinematic wave, masking gun, whatever they need to do. And subsurface flow is basically doing the same thing but a little bit slower, with a multiplier. It's the same routing, the same calculation, but that multiplier can be calibrated.
Okay. Anybody else have any questions? I'm panning the audience here. Yeah, go ahead.
Thank you so much for your presentation. It was very insightful. You talked about capacity building and some of the people you are training or you're interacting with are in Africa. So at the very beginning of your presentation or some slides, you talked about post-evaluation, if I got the word right, which means you need to check the context you are working in. So in Africa, the challenge I see is usually data. It's a poor data environment. So how, what are you recommending as the right hydrological model for Africa, considering the lack of data? And what challenges have you encountered interacting with people who are on the ground? Yeah. So yeah, it's more on the data challenge. That's what I wanted to.
Right. Yeah. So here's the thing. So about the observation data, right? Like a stream flow, the Africa might not have that much density. So here's a good thing that is Princeton University, they provide a global river discharge reanalysis. And it has been proven to be quite accurate in some places. They have evaluation over continents and by continents. So that data set can be used, and that data sets that data set's available online, and totally can use that one as the reference for you to calibrate the model into, right? That's for the observation of stream flow. But if you're talking about other data, right, like other data that requires for the model, want a model that has minimal required data as possible. So as far as the ones that it has doesn't have that much requirement, the first is the SWOT model. SWOT model doesn't have that much data requirement. It's very simple, and you don't have that much. Most of the data you can get it from like a hydro shed, right? Hydro shed, those data basically works for SWOT. And basically that's it. And a lot of like global satellite precipitation, GPM, that's available. You can totally use that. So SWOT is definitely one of the least data required model there. And another one is the CREST EF5, which we have successfully applied to the African region. Because one of the reasons is just it doesn't really require that much data to input in there.
Okay, question over here, Katie.
Hi, thank you.
Hi.
I really appreciated your discussion on flood maps at a local scale and in general. And you didn't even get into looking at FEMA flood maps, which we know don't include precipitation, induced flooding in them. But
Right.
I'm wondering, from that discussion, how do you really, what do you think the best practices are in communicating the strengths and uncertainties in flood maps? In the sense that everybody wants a flood map, right? And flood maps
Right.
show different things, and kind of grappling with that idea of the trust from the public in
Right.
communication when flood maps, from many trusted sources are showing very different results.
Yes. Actually, the other day I was talking to the local. I'm from Oklahoma. There's local Native American tribes. They were talking about. I was just talking to them. Hey, the FEMA map that you're using, they're using the data from 70s and 80s, right? But that's totally different. Even the landscape is totally different from right now. So if the FEMA said you're not in the flood zone, you're probably in the flood zone right now, but you just don't know yet. So here's the thing, because FEMA is a government agency, right? Your government agency tend to move a little bit slower than the research. That's understandable. And also the methodology is totally different. So what FEMA does, they take the water, they carefully measure the channel. They measure the river geometry, river channel geometry, and they assume there's a 100-year flood coming through that channel. Then they use the HACRAS to simulate how much water will overspill to your floodplain, to the floodplain. That's how they generate the data. So basically, they give assumption of there is a 100-year flood in that channel, and the water will spill out, and that's exactly how that's calculated. But in current phase, currently most of the literature, especially 2D inundation, you are more likely to consider this overland flood, right? Overland flood, which is it's just a rainfall accumulated over there. It doesn't have enough time to get into the channel, and it accumulates over there. So I think that's a methodology. It's very, very different. And but I don't think we can convince FEMA to get rid of HACRAS, because Army Corps designed that. That's the standard procedure for them to do. But I do think local agencies. That's what I suggest to the Native American tribes, that they need to learn to use those inundation model and update their own map and intercompare with the FEMA's floodplain map. Again, that's the reference, right? It's not truly accurate enough to say, hey, at next event, your house gonna be flooded, right? It's not there. But at least that's something you can update. You can update for yourself instead of relying on FEMA to produce another national level of map, because that's gonna take years
So I agree with you entirely that the FEMA's working on things and there's a long way to go there. But after looking at products like Fathom as well, for river systems that I'm familiar with, they don't include engineered structures where there's a lot of flooding from those. So thinking about, I think my big picture question here was, right, how do you communicate that uncertainty across these different products that maybe some show flooding better than others for different reasons, like you mentioned, but should the public believe none of them? Should they believe one of them, right? How do you communicate strengths, weaknesses, and, what we should believe, I guess?
Right. I think like Fathom, well, to be honest, personally, I think it just, it's a little bit too ambitious to do that globally right away. Because my opinion is that the local agency need to have their own system, because the local agency has their own, they have their own system, they have their own data, they have better idea if the data is right or wrong. Because some of the data just simply not available if you try to apply for a large scale, and those data treatment it's especially increasing if you're thinking about every single details about the streets and the buildings and landscapes and gardens, right? But if you come down to local agencies and local, they know the area better. They have better survey. They have better data, and locally, well, some of them, some of them not, right? But if they can apply those data to the local, to their own capacity, then they can do them by themselves. Well, the model once it's running, right? So I think that's the solution, because if it's hard to rely on a global, like Fathom, they do globally, and they don't have the time to look at those details. Even like a national water model, all right, they are in Tuscaloosa, they have an entire building and people looking at it, and they are looking at each ridge, and each ridge, it takes multiple years. It's hard for like one agency to do it all. That's what I'm understanding, because those are small things, like a little barrier, a little levee is big enough, right? But a little barrier like a roadblocks, that's not there. But the little roadblocks might change this neighborhood and that next neighborhood having the flood difference or not. You look at that much, like a 10-meter detail or 3-meter spatial resolution. So that's there. So I do think it's hard for like one agency to do that. I think the local agency need to build up that capacity. That's what I'm thinking.
Yeah, and I mean, I totally agree with you there, but I also think a lot of local areas lack the capacity to do this by themselves all the time. So
right.
I enjoyed this discussion. I got to run and pick up my baby. So.
Yeah, the
That's
time
important. That's
is
important.
basically
Yeah.
up. Unless somebody else has a really quick question,
Yeah,
we'll do it. So thank you a lot, Dr. Chen.
Thank you.
Okay.
Thank you for having me.
Sorry, long distance, but another time.
Yeah.
Okay, next week, the speaker will be Dr. Samuel Smith from the Department of Soil, Water, and Ecosystem Science at the University of Florida, a local guy. And